In the previous section, various properties of a fully developed laminar pipe flow were discussed. Now, in this video, we are talking about the fully developed turbulent flow. It is necessary to obtain the similar information that we got for the laminar pipe flow for the turbulent pipe flow, because this is another scenario in the real life. So, but turbulent flow is very complex process, and the field of the turbulent flow still remains the least understood area of fluid mechanics, because the turbulent flow involves randomly fluctuation parameters. So if we look at these figures right here, so these are the laminar section that we have. This is the transition, and we can see it just has a little turbulent and also a mix between laminar and turbulent. And here we have lots of fluctuation, and because in this region and we can see that the Reynolds number is greater than 4,000. This is why we call this area turbulent. And if we look at the zoom in of the part of, I mean, this turbulent flow here, this u this u here is the time average of the velocity, and then this u prime here, we call it the fluctuation. So it means that the turbulent flow, the velocity is involved with the fluctuation. And but there are always, there are some advantages and disadvantages of turbulent flow. The advantages of the turbulent flow is the mixing process and heat and mass transfer process. It going to be enhanced when we have turbulent flow if we compare it to laminar flow. But then there are also another, some disadvantages of the turbulent flow. For example, the drag is it increased the drag, so it is not good for the aerodynamic aspect. And also we need to have more power and energy in the turbulent flow. So so now we talk about how turbulent flow is complex and it's a difficult topic. It was all because of the randomly fluctuation parameters that is involved in the turbulent flow. So now, when we want to consider the head loss in the pipe flow that has the turbulent flow in it, the head loss is a combination of we call it head loss, major loss, and then the minor loss. So, and we can see it right here, right? So, but if you remember, for the laminar flow, we just have head loss, and it doesn't come, it's not, it wasn't a combination, right? So for major loss, if we come here and talk about the major loss, let's if we performing dimensional analysis, then the resulting of the pi terms going to be like this, right? These are all the variables that we say that the pressure drop depends on it. So, for example, if we consider a steady and incompressible turbulent flow in a horizontal ramp pipe, and we consider the diameter d for the pipe, then the pressure drop through the pipe is dependent of velocity and then diameter and then length. And this one here We call it it's roughness, right? So we call it roughness, and it's usually in millimeter. And then also this one here, we know that this is density, and then this is viscosity as well. So we also can say that this is the turbulent contribution, and also this viscosity is the laminar contribution. Let's see what we have here. So now, by using these variables right here and considering the dimensional analysis, these are the pi terms that we get, right? So this one, we call it relative roughness. And if we look at figure 8, figure 8 point, I think 19, then you can see the value for it. And then so let's say we have this formula here, and if we assume that the pressure drop is proportional to the pipe length, then we're gonna have this formula right here, right? And then if we have this one, and we consider the friction factor as this value here, then we can write down the formula as this, right? And if we have a laminar flow, we use that one for F. And if we have, and yeah, because in the laminar flow, the epsilon is not important. It means wall roughness. So now this is also what we have here. Oh, let me talk about this one. You know, this is the rough wall. If we can just look at this part here, right? This is just a small. If we zoom in the layer, and that is the wall layer. So this is how we can see that the rough wall there. So then we call it. So this is from here to here is epsilon. And if it's a smooth wall, this is how the epsilon is really small. And now if we apply the energy equation for a steady and incompressible flow in this for this pipe right here, if we write it down the energy balance and just simplify it, then we get these for the major loss. So this is the formula for major loss right here. And then we also call this formula as Darcy-Weisbach equation. This is another name of it. So, and also we are going to use yes, we are going to use table 8.5 to obtain the surface roughness, and also the Moody chart that when we solve the question, we are going to use that Moody chart in this chapter to determine the F, which is this friction factor right here. All right. And then if now, so we talk about the major loss, and now we're talking about the minor loss. So minor loss is happen mostly due to flow past valves, bend, teeth, etc. So um, so let's first define KL. This KL right here, we are going to name it as loss coefficient K, so which is strongly dependent on geometry. For example, mm, geometry, I mean, of the pipe. So, and if we want to get the value of it, we need to take a look at figure 824 and figure 830. So these are the figure that we are using for getting the value of KL. And if we just cross multiplication that one, this is the loss minor that we get, minor loss. So this is also the minor loss. And then also, another important thing is that it's not always the case that we have a round pipe. Sometimes we have a non-circular conduit. So in this case, we just need to, instead of the D in the Reynolds number and in the major loss, so in the Reynolds number, so we just put this DH here, right? So we replace the D in the Reynolds number formula and in the measure loss with DH. Then we can use all of the formula above for the non-circular pipe, right? So now these are some examples for a little more complex pipe. So these multiple pipe system so can be classified to the series and parallel flow. For example, this one is series, right? And this one we can see that these are parallel, right? And it's also like we are using the circuit system in the electricity, right? So if we consider that definition, so from here, and if you just apply the conservation of mass, you can see that Q1 right here, this is 1, this is 2, and this is 3. So Q1 here is equal to Q2 plus, sorry, equal to Q3, right? And then also the head loss from A to B, from here to here, is going to be the sum of all of the losses that we have, right? And for this one, so we have a flow that coming here and then it divided to 3 sections, right? So it means that then the Q1 is equal to Q1 is equal to Q2 plus, so not Q1, Q, if we consider this one as Q, right? So this Q is equal to Q1, Q2, and Q3. So Q1, Q2, and then Q3. And then also the combination of the losses. So we can say that the losses here is equal to losses here. I mean, this pipe here and this pipe here and this pipe here, then the losses are the same. So we can write down HL1 is equal to HL2 is equal to HL3, right? And then for this particular pipe right here, that this and we call this multiple pipe system as loop. This is the name of this kind of this type of the multiple pipe system. And also here we can see that the Q1 is going into the pipe, and then it divided to flow in the in the pipe 2 and pipe 3. So in this case, then Q1 is equal to Q2 plus Q3, and then also the head loss at for pipe 1 and 2 should be equal. So if we write down the energy equation from A to B, then this is what we get. So PA over gamma plus VA squared over 2G plus ZA. So nothing fancy till here. So here we have PB over gamma plus VB squared over 2G plus ZB plus H loss of 1 plus H loss of 2. So also we said that H loss of 2 and 3 are the same. So another way that we can describe it is PA over gamma plus VA squared over 2G CA equal to PB gamma plus VB squared 2G plus ZB plus HL1, and then here we can also write it down as HL3. So the only term that is different is these two, and this is actually the same. So this is how we can write it down. So we are going to solve some question on it in the office hours.